Alright, welcome to this week's homework review. This was a homework assignment that covered mostly Chapter 8, which is ideal gas laws, but also had some very end material in Chapter 7, namely lattice energies, which is everybody's favorite topic. As you can see, the average this week was 9.47 out of 12. A little bit lower than the past, but I suspect it's because of the lattice energy questions, which a lot of us had trouble with. So we're going to spend some time going over some of the problems from this week where the success rate for this section was around 50% or less, so we'll go over some of the ones that we had the most difficulty with. As I said, it's going to include a bit about lattice energy before moving on into the newer stuff about ideal gases. Alright, so the first couple problems we'll go through are sort of your typical run-of-the-mill lattice energy calculations. We're going to give you a bunch of experimental parameters, ionization energies, enthalpies of formation, all this stuff, and we're going to ask you to calculate lattice energy for it. So we have here the hypothetical compound MX, which means it has one metal and one non-metal in the formula. That's what that means. And we want to calculate lattice energy from the information below. Now there's two ways to do this. As I sort of introduced in class, there is a formula method for doing this where the lattice enthalpy is going to be the formation enthalpy, and then we're going to subtract a bunch of terms from that. So what I should say is that this is for the compound M with a subscript M, X with a subscript X, where lowercase m and x are going to be the subscripts that tell you how many of each metal and non-metal are in the formula. Okay. So if we have this generic formula for an ionic compound, the lattice energy is going to be given by the enthalpy formation. And then there's going to be two terms associated with the metal, each of them modified by the coefficient m. So m times the ionization energy for the metal minus m. I skipped a step, sorry. We can do this in any order we want, but it makes more sense to do it this way. So it's going to be m times the sublimation enthalpy, or atomization enthalpy, and then minus m times the ionization energy for the metal. So these are the two terms associated with the metal. This delta H of formation is for the compound itself. And then we have two terms associated with the non-metal. And these two terms are going to work whenever we have our non-metal existing as X2 gas. So whenever the standard state of the nonmetal is X2 and that standard state is a gas, which is true for most nonmetals that we make ionic compounds with, this will be the way the formula goes. So we're going to have X over 2 times the bond dissociation enthalpy, and then minus X times the electron affinity of the nonmetal. So these two terms again associate with the non-metal X, this one being the bond association, and bond dissociation enthalpy being for X2. So this is the equation we have. We have a delta H formation, which we're never going to modify or change the sign of. We're going to subtract two terms for the metal, sublimation and ionization energy. And then we're going to subtract two terms from the non-metal. Bond dissociation enthalpy, which is going to be multiplied by X over 2, where X is the number of non-metals, because this one is associated with the molecule X2. And then minus X times the electron affinity, where this again is the energy required to gain electrons. So if we look at the information in this problem here and we try to find these terms, one of the challenges is that we're not always going to use the same abbreviations. I'm using some abbreviations here for all these terms, but they're not necessarily going to be labeled as that in the given information. So let's look at what we have. So remember that delta H of formation is the amount of energy required to form the compound from its elements, and so that's going to be this term here. As I said, we'll sometimes abbreviate them as delta E's, but really delta H is the more appropriate term now in this part of the course. But this one's going to be delta H of formation. Elements going to the compound, metal plus X2 going to MX. So that's our delta H of formation term. Sublimation enthalpy is going to be the energy required to go from solid to gas phase for the metal. So this is how we're going to label that. That's going to be M solid to M gas. The next term is ionization energy for the metal. That's this one here, which is labeled as such, so no difference in label there. And then the two terms associated with the non-metal are bond dissociation enthalpy. Again, that's the enthalpy change required to break the XX bond, or break or decompose 1 mole of X2 into 2 atoms of X, 2 moles of X. So that's going to be this term here. This is the bond dissociation energy, or enthalpy. And then finally, the electron affinity is labeled as such. That's the amount of energy required to add electrons to the nonmetal. So this is our electron affinity term. So those are going to be the 5 terms we need for this equation down here. What we sometimes do to sort of test that you're actually following what's going on here and to make sure that you're really understanding this is we're going to give you some extra information. So the ionization energy of the nonmetal we don't need at all because the nonmetal is gaining electrons, not losing electrons. So now we can just start and we can put the numbers in. So delta H of formation is going to be minus 103.3. And then our compound here is MX, so it has 1 metal and 1 nonmetal. And so what we're going to get then is for the sublimation enthalpies, we're just going to have 1 times that. So sublimation enthalpy is this one here, 66.5. We have 1 times ionization energy, which is 495. We have X over 2 times the bond dissociation energy. X is 1, so it's going to be 1/2 times that bond dissociation enthalpy, which is 184. Then we have 1 times the electron affinity, which is minus 366. So when we put those numbers in, we get, let me just see what we get here. I got minus 390.8 kilojoules. So you should get a negative number every time you do this. And this would be the number that we get here, minus 390.8. So that's one way to do it, is just to use this equation, learn which terms you have to use and which order they come in. Now the way to visualize this a little bit better is to draw out the whole Born-Haber cycle, as we call it. So this is where we start again with the ionic compound MX here at the bottom, and we're going to do a series of steps that are going to break up the ionic compound into its ions, and then we're going to recombine those, which is the energy that is associated with lattice enthalpy. Alright, so when we do this, the first step is going to be to break it up into its elements. So the standard states for the metal are going to be M solid, and then it's going to be 1/2 X2 is the standard state for the non-metal in this case. You see that there's no X2 liquid or solid terms. Everything is in terms of X2 gas here. So that's going to be the standard state of our elements. We break up into that. This is going to be then negative delta H of formation, which for this compound is going to be 103.3. The next step is going to be to sublimate and ionize the metal. So we're going to take the metal that's a solid and make it into gas phase first. And so this term here is sublimation enthalpy, which for the metal, as we said, was 66.5. Next step is to ionize the metal. This is a 1-to-1 ionic compound, so it's going to be just losing 1 electron. So go to M+. So we have ionization energy of the metal, which was 495, I believe. Sorry. Alright, and then the next step, that's the last endothermic step, is going to be to dissociate X2 into X. So we're going to take this 1/2 X2 and we're going to break it up into just 2 X's. So 1/2 X2 goes to 1X. Keep everything balanced, and this is going to be then 1/2 times the bond dissociation energy. Because again, we're doing this for 1/2 of an equivalent of that X2, 1/2 moles of X2, so we need to modify that by 1/2. So that's going to be 1/2 times 184. And I'll just leave units off universally for now. So that's going to be 92 kilojoules per mole. And then coming back on the other direction, all the exothermic steps, we have an exothermic step which is the recombination of, or not the recombination, but the combination of X with the electron. So giving this electron to X to form X minus. That's what we refer to as the electron affinity of X, which in this case is minus 366 kilojoules per mole. Hopefully that's the number, if we have that right. And then finally the last step, which is what we're solving for, is combining the two ions, the gas phase metal cation, the gas phase nonmetal anion, combining them to form our solid ionic compound MX. And this term here, which is our unknown, is our lattice enthalpy, which is what we're solving for in this case. So then what we're going to do is we're going to add all of these numbers together as we go around this cycle, and the sum of those is going to be equal to 0. So 103.3 plus 66.5 plus 495 plus 92, and then plus minus 366 plus the lattice enthalpy. The sum of all of those has to equal 0, and when we solve for lattice enthalpy we get the same thing, minus 390.8. So mathematically these two work out the same. If you're more of a visual person and you like to write out all the individual steps and see where we're going as we do all these different individual elementary steps along the sequence, this is a helpful way to do it, but it does take a bit more time. So I went through that here just to show you how we can draw these Born-Haber cycles, but in reality I think to save some time learning how to use these equations up here and which terms to use and how to combine them is probably going to be faster for most of you. Alright, so let's do one more example here where we have, in this case, M2x. So the only difference here is that since it's M2x, we have two metals and one nonmetal in the formula, so those are going to be the terms that we use to modify in those equations. And the other slight difference is that our nonmetal anion is going to have a 2- charge to balance this, so it's M2x2-. So that doesn't really change the math at all. We just have to be aware that the electron affinity set for X is going to involve 2 electron affinities, adding 2 electrons to the nonmetal. So again, we can still use the general formula though, which is that lattice enthalpy is equal to delta H of formation for the compound that we're interested in, which in this case is M2x. We subtract 2 terms that are associated with the metal and multiply them by the number of metals we have. So M times the sublimation enthalpy minus M times the ionization energy for the metal. And then we're going to subtract 2 terms associated with the nonmetal. It's going to be X over 2 times the bond dissociation enthalpy of X2, and then minus X times the electron affinity of whatever the nonmetal is, X. Alright, and the only difference here is that this electron affinity step in this problem is actually going to be 2 electron affinities because, again, we're forming 2- anions. We're adding 2 electrons to it. So we have to make sure that is given to us correctly in the problem, or that we account for both of those terms. So again, looking at the different steps here, the formation enthalpy is going to be the formation of the compound from its elements, which is going to be this one here. Sublimation enthalpy is metal solid to metal gas, so that's this one. Ionization energy for the metal is labeled exactly like that. So those 3 terms are we're going to use bond dissociation enthalpy for X2, which is this one here, X2 going to 2 X's. That's bond dissociation enthalpy. So make sure we just have all the labels correct. And then again, as I said, this is going to be a sum of 2 electron affinities, and we're giving this number to you as a sum of 2. And usually when it's 2 electron affinities that we're considering, it's going to end up being an endothermic step, a positive number instead of a negative number, as we usually see for a single electron affinity. So we still use that exactly as is. We don't change the sign of it, but be aware that this number, the electron affinity, could be a positive or negative number, depending on the element and depending on whether it's adding a single electron, which is typically exothermic, or adding 2 electrons, which is typically endothermic. So again, don't be thrown off by that. We just have to use the number in this equation exactly as it's given to us. So then when we plug everything in, we have delta H of formation is minus 1232. We have two metals in the formula, so we're going to modify sublimation enthalpy and the ionization energy by a factor of 2. So sublimation is 331. Ionization energy for the metal is 373. We have one nonmetal X, so we're going to subtract 1/2 times the bond association enthalpy, which is this term here, 252. And then minus X, which is just 1 times the electron affinity, where again it's going to be a sum of 2 electron affinities, 278. And this time we should get a much larger or more negative lattice energy with these numbers here. So let me work out the math real quick. So what I got for this one was minus 3044 kilojoules per mole. Okay, so that'd be the number we would put in. It's always, lattice energies are always going to be negative, so if your answer is not negative, check your work or at least check your sign. And it should be, in most cases, a relatively large negative number as well. So, alright, so that's another example of how I do this. I'm not going to draw out the whole Born-Haber cycle again because it takes forever, but these are the numbers we want to use for this one. Again, a pretty standard example where the only difference was we had two metals in our formula, so we had to modify these two terms by a factor of 2, and then recognize that this last term here is actually a sum of 2 electron affinities. Again, as we gave you before, we gave you the ionization energy for X, but we're never going to use that. Ionization energy refers to losing electrons. The nonmetal, when we're forming an ionic compound, will only be gaining electrons. Alright, so those are two questions on how to calculate lattice enthalpy. And again, that's one of those things you're just going to have to practice a lot to get good at, because there will be 1 or 2 test questions on that in the upcoming exams. Now, the next type of question we have for lattice enthalpy, which we also had a little bit of trouble with, was just comparing lattice enthalpies. So here we're looking for which of the following compounds would have the greatest or most exothermic, most negative lattice energy. So when we're doing these types of comparisons, what we have to recognize is that the lattice enthalpy is proportional to the product of the two charges divided by the distance between them, r. Alright, so we're again, Q1 and Q2 are the charges of the anions and the cations that make up the ionic compound, the charges of the ions. R is the, I guess I should just say the distance between the ions. Which is governed by the size of those ions. So it's going to be basically the sum of the radii of the positive and negative. So the larger the ionic radii, the larger the distance, smaller the ionic radii, the smaller the distance. Now when we're evaluating these types of problems, the first thing we want to look at is charge. So we're going to do the charge first, because if the product of the two charges is, it's going to be either Q1 and Q2 are either +1 and -1, or Q1 and Q2 are +2 and -2. Those are the types of compounds that typically compare. So that's going to differ by a factor of 4 if we're changing the charge from +1 -1 to +2 -2. The radii will never differ by that large of an amount. That's more of a subtle perturbation. So we're going to look at charge first. If we're looking for largest lattice enthalpy, which we are here, we want to have the highest charges. And then if we have two choices that have the same charge and they're both the highest charges, then we have to compare the radii. So looking at these ones here, we have to go to the periodic table to figure out where these are. Magnesium oxide, we have to figure out what the charges of the ions are there. So bring up our periodic table, as I think we should all know by now. Magnesium here is in the second column, so it's going to be a +2 cation. Oxygen's in the third to last column. Second to last column. Anyway, group 6 for oxygen, which is going to be -2 anions. So magnesium oxide is a +2, -2 ionic compound. And then if you look at the rest of these, LiF, NaCl, KBr, cesium iodide, all of those are going to be +1, -1. They have lithium, sodium, potassium, and cesium, all +1 cations paired with fluoride, chloride, bromide, iodide, all of our -1 anions. So the rest of all of these have the same charge of +1, -1. And in this case, since we're looking for the largest lattice enthalpy, we're looking for the highest charges, and the only one that has +2 and -2 charges is MgO, so we can automatically assume that's our answer. We don't even have to compare radii here. Comparing MgO to LIF, those are going to have, some similar radii, but it doesn't even matter what that comparison is because the charges for this one are higher. So when we're comparing lattice enthalpies, look at charge first. If you want the highest lattice enthalpy, you want the highest charge. If you want the smallest lattice enthalpy, you want the smallest charges. And then if you're asked to compare two that have the same charges, that's where you have to look at the distance, which is inversely related to lattice enthalpy. Alright, that takes us to the end of that topic. The next several questions we're going to do to close this out are going to be dealing with gas laws. So the first thing we learned about gases was pressure, which is force divided by area. It's exerted by all gases in a closed container. And we learned a little bit about how to measure it. And so that's what this first question deals with. And there was a few similar ones on the test or on the homework like this. So here we have a barometric pressure of 0.956 atmospheres when the mercury level in an open-end manometer was 132 millimeters higher on the side open to the atmosphere than on the flask side. What was the pressure of the gas in the flask in torr? So there's a lot of information in this problem, and the first thing that's going to help us, as the hint tells us, is let's sketch the apparatus. So here we're measuring pressure in an open-end manometer. So what we have is a sample of gas, and it's going to be connected to a U-shaped tube. I didn't draw that particularly well, not surprisingly. There we go, let's do this a little bit better. Okay, so we have this U-shaped tube, the gas is in here, and on the other side is going to be atmospheric pressure pushing down because it's an open-ended manometer, so the other end is open to the atmosphere. And we're told here that the atmospheric pressure, which is also referred to as the barometric pressure, is 0.956 atmospheres. And then we're said that the mercury level is higher on the side open to the atmosphere. So when we sketch the mercury level out, it's going to look something like this. And this difference here in distances was 132 millimeters. Now the fact that it's higher on the side of the atmosphere means that the gas is pushing down harder than the atmosphere. That causes this imbalance where this has a higher pressure than the atmospheric pressure. And so what that means is that the pressure of our gas is going to be the atmospheric pressure plus the difference, which is 132 millimeters. So the first thing we have to do is, before we add these two together, I guess I'll write this in more general form first. So it's going to be atmospheric pressure plus delta H. It's plus because, again, the gas pressure has to be higher than atmospheric pressure to make the mercury lower on the side of the gas than it is on the side of the atmosphere, which is just going to be then the sum of these, atmospheric pressure plus this delta H, this difference in height here. But they have to be in the same unit, so we want them to be in millimeters of mercury. So we're going to have to multiply this times 760 millimeters of mercury per 1 atmosphere. So the atmospheric pressure in the correct units is going to be 726.6. So that's going to be our atmospheric pressure, 726.6 millimeters of mercury, and then the pressure of the gas is going to be larger than that by 132 millimeters. This comes out to 858.6 millimeters of mercury. And remember that millimeters of mercury and torr, which is the unit we want, are equivalent to each other. We'll round to the correct number of significant figures and write this as 859 torr. Okay? So that's how we approach this one. It's just sort of getting used to how these pressure measurement apparatuses work. And in an open-ended manometer, it's a competition between the gas pressure and atmospheric pressure. And in this case, the gas pressure must be higher than the atmospheric to cause the mercury column to be lower on this side than on the atmospheric side. And then we just simply have to add the two together, making sure they're in the right units. Alright, so that's how we measure pressure. The rest of the problems are going to deal with some properties of pressure related to these different gas laws. And so the first type of ideal gas law problem we could have is just to use the ideal gas equation, PV equals nRT, and solve for one of the unknown parameters here. So here we have 8.99 times 10 to the minus third moles of argon. We have a 415 milliliter container and it's 52 degrees Celsius, and we want to know what is the pressure in torr. Okay? So in this problem, we're not really changing any of the properties. We're not changing the number of moles. We're not changing the volume. We're not changing the temperature. We're just giving you a set of 3 conditions and asking you to solve for the 4th parameter, which is pressure. So when we rearrange the ideal gas equation, pressure is equal to nRT over V. And now we just have to plug in all of our numbers, making sure they're in the correct units. So N is number of moles. That we're not going to change the units of ever. It's just 8.99 times 10 to the minus third moles. R is universal gas constant, which is on our periodic table, 0.0821 liter atmospheres per k mole. And so this tells us the rest of the units we need, which we need our volume to be in liters and our temperature to be in Kelvin. So our temperature here is 52 degrees Celsius. So the temperature in Kelvin is going to be 52 plus 273, which is 325. So we need to make sure that temperature is always in Kelvin whenever we're using gas equations. 325 Kelvin. And then divided by the volume. The volume has to be in liters for the ideal gas equation. So it's going to be 415 milliliters divided by 1,000 to convert from liters to milliliters to liters is 0.415. So that's going to go down here in the denominator, 0.415 liters. And so what this comes out to in atmospheres is 0.578. So that's the pressure in atmospheres, but we want the pressure in torr again. So the pressure in torr, we have to take this final answer and convert it. So it's going to be 0.578 atmospheres times 760 torr per 1 atmosphere. That's the key conversion factor for pressure units that you're going to want to know. So 0.578 times 760 is 439 torr. And that would be the number we would put in. Alright, so this is again just using the ideal gas equation to solve for an unknown, where we're going to give you the other 3 and just have you solve for one of those, either pressure, volume, number of moles, or temperature. Now the more common way that we use the ideal gas equation is going to be represented in these next couple questions here, which is where we're changing some of the conditions. So here we have a balloon filled with helium. We're telling you that the volume of that balloon is 1.5 liters. The pressure is 90.5 kilopascals. Kilopascals is another unit for pressure, not as commonly used. And then the temperature is 25 degrees Celsius. We want to know what will the volume of the balloon be when the pressure is 35 kilopascals if there is no change in temperature. So for all of these different relationships, we have some equations we learned. We had Boyles Law, Charles' Law, Avogadro's Law. We don't have to necessarily remember those individually. We can just start with PV equals nRT. And then everything that's constant, we move over to one side of the equation. Everything that's changing, we move to the other side. So in this problem, we're told that the pressure is changing, and we're solving for what the final volume will be. So we know that pressure and volume are changing. The number of moles is constant because it's a closed container. It's a balloon. So unless our balloon's leaking, we're not going to lose any moles of gas. And we're told that temperature is constant as well, directly in the problem. There is no change in temperature. So we're going to move pressure and volume over to one side, and so we don't have to actually rearrange the equation at all. It's just going to be PV equals equal to nRT, and this is then going to be constant, because everything that's constant is on one side of the equation now. Or alternatively then, P1V1 equals P2V2. Now this is what's called Boyles Law. We learned that first, the relationship between pressure and volume. But you don't have to remember that separately. We know that these are the only 2 that are changing, so as long as they're on the same side of the equation, everything else we move over, and then the initial and final conditions have to be equal to each other. And so what we're looking for here is the final volume V2, which is just going to be P1V1 over P2. And for these types of problems, we don't even necessarily need to convert the pressure, because as long as P1 and P2 are in the same units, those units will cancel out. The ratio of the 2 pressures will still be the same. And so what we have is P1 is 90.5 kPa, kilopascals. V1 is 1.5 liters. And then P2 is 35 kPa. We don't have to convert the units again because the units cancel out and we're left with an answer in liters. So we just multiply and divide and get an answer of 3.88. Alright, so for some reason we did particularly poor on that one, but that was just straightforward application of, in this case, Boyles Law, which we can derive from the ideal gas equation. The next one that's similar to this is a little bit more complicated because we're changing a couple parameters. So here we have our initial volume, 6.36 liters. Initial temperature is 55 Celsius, pressure 0.875. We want to know what volume will it occupy if we change the pressure to 1.05 and the temperature to 25. So here, pressure, volume, and temperature are all changing, and because we're not told anything about it, we can assume that the number of moles is constant. Alright, we're not told how many moles there are, we're not told that there's any addition or subtraction of gas from the sample, so we assume that moles is constant. And so when we start with the ideal gas equation here, we want to move pressure, volume, and temperature over to one side. So pressure times volume divided by temperature is equal to nR, and this product here, N times R, will be our constant in this case. And so the form of the equation we want to use is that P1 V1 over, T1 equals P2 V2 over T2. So pressure, volume, and temperature are all changing. We can rearrange the ideal gas equation, moving all three of those to one side and setting the initial and final sets equal to each other. So now what we're solving for here is, again, final volume, V2, which is going to be P1 over P2, is the ratio of the two pressures. So we're just rearranging this equation to solve for V2, and then it's going to be T2 over T1, the ratio of the two temperatures, and then multiplied by V1. Alright, so I wrote them in a different order, but again, just to show you that it's the ratio of the two pressures, P1 over P2, times the ratio of the two temperatures, T2 over T1, times the initial volume, V1. So now we can just start plugging things in. And again, for our pressure, as long as they're in the same units, it doesn't matter what they are. So here they're in atmospheres anyway, which is the standard unit. So P1 is 0.875. P2 is our final pressure, 1.05 atmospheres. Now the temperatures do need to be in Kelvin though, so that's the one unit you can't play around with. So the temperature is initially set 55 degrees Celsius. Converting that to Kelvin by adding 273, that's going to be 328 Kelvin. And then the final temperature is 25 Celsius, which is 298 Kelvin, adding 273 to that. So it's going to be T2 over T1, so we're going to put 298 Kelvin over the initial temperature, which is 328. And then the initial volume V1 was 6.36 liters. So that goes up here in the top. So when we multiply all of this out, what we should get is 4.82 liters. So the volume shrinks because the pressure is getting larger and the temperature is getting smaller, so both those contribute to decrease in the volume by a small amount of 4.82. So this was sort of a combined gas equation where we had to take three of the parameters, move them to one side, with two of them changing, in this case, both the pressure and the temperature. Alright, but that's the approach we want to use for all of these. We start with the ideal gas equation, we find the variables that are changing, we move them to one side, and that's going to then get us started where we need to go. The last two here deal with other aspects of the ideal gas law, and so one of them is going to be gas density. And so here we're just asking you to calculate the density of carbon dioxide gas at minus 25.2 degrees Celsius and 98 kilopascals. So what we learned before is that if we start with PV equals nRT and we rearrange the equation, what we get is an equation for density, which is, again, the definition of density is mass over volume, and this is equal to pressure times molar mass divided by RT. So this is just, again, a rearrangement of the ideal gas equation to solve for density. Now, because we're using the value of R here, P needs to be in atmospheres, and temperature needs to be in Kelvin still. So we first have to convert our parameters to the right unit. So our pressure is 98 kilopascals. So the pressure in atmosphere is going to be 98.0 kPa. And then the conversion that we should also learn, because it's going to come up from time to time, is that 1 atmosphere is 101.3 kilopascals. So 98 kPa is equivalent to 0.967 atmospheres, so close to 1 but not quite. So that's the pressure we're going to put into this equation, 0.967 atmospheres. The molar mass of CO2, so this is carbon dioxide, CO2, and so the molar mass of that is 12.01, which is the atomic mass of carbon, plus 2 times 16, which is the atomic mass of oxygen, which comes out to 44.02 grams per mole. So that's the molar mass we're going to put in, 44.02. Then we divide that by RT. R is the universal gas constant, 0.0821. And then the temperature has to be in Kelvin. So if we add 273 to minus 25.2, we get a temperature of 247.8 Kelvin. And so when we solve for the density, which will be in grams per liter, we just multiply these out and divide. 0.967, 44.02. I got an answer of 2.09 grams per liter. I don't remember if this was multiple choice or free response, but that would be the answer we would put in, 2.09. So again, we're using just the ideal gas equation here, but rearranging it to solve for density, and we just have to make sure that pressure is in atmospheres, molar mass is still in grams per mole, temperature in Kelvin, and we just use this equation to get density directly. Alright, the last problem we're going to deal with is gas stoichiometry. So we have this equation here, lithium plus H2O going to H2 and LaOH. We do need to balance it, so let's make sure we write it out in balanced form. And so I think the way this is going to work is hydrogen is unbalanced right now. So I think that we're going to put we could balance this as a redox equation too if we wanted to actually, but we'll put a coefficient of 2 there, 2 there, and 2 there, and that should balance everything. Alright, so somehow we needed to balance that, and if we put coefficients of 2 in front of lithium and water and the product lithium hydroxide, that will be the correct balance equation. Alright, so what we're looking for here is how many liters of hydrogen gas can be produced at 18 Celsius and 725 millimeters if we're reacting 3.8 grams of lithium with excess water. Alright, so if we're using ideal gases, we're forming a gas as one of our products, in this case hydrogen. What we have then is we want to again think of PV equals nRT. And so what we're doing in gas stoichiometry problems is we're going to find the number of moles, and then we're going to relate that to other parameters using the ideal gas equation. Okay? Sorry, my tablet's lagging here. Give it a second to catch back up. Alright. So the first thing we're going to do is we're going to find the moles of hydrogen that form. Or alternatively, we read that as N in the ideal gas equation. And that comes directly from stoichiometry. So we're using 3.08 grams of lithium, and we're going to find out how many moles of hydrogen form from that. So we convert grams of lithium into moles using its atomic mass, which I think is 6.94. So that's the atomic mass of lithium, 6.94 grams per mole. So that converts into moles of lithium. We look at the balance equation. We're going to form 1 mole of H2, because there's a coefficient of 1 per 2 moles of lithium. So that has a coefficient of 2. And so this gives us how many moles of hydrogen we're forming. which is 0.464. And then what we're looking for here is how many liters can be produced. So we're going to solve then for the volume using PV equals nRT. So the volume of H2 is going to be the number of moles. Again, we're looking for hydrogen here. Moles of H2 times RT divided by the pressure. And so the moles we just found is 0.464. R is 0.0821. And because we're using R, temperature needs to be in Kelvin. So it's 18 degrees Celsius, which is going to be equivalent to 18 plus 273, which is 291 Kelvin. So that's the temperature. And then our pressure needs to be in atmospheres because we're using the ideal gas constant, which is in atmospheres. So the pressure in atmospheres, again, we have to convert from torr, or millimeters of mercury in this case. So the pressure in the atmosphere is 725 millimeters of mercury, which is equivalent to 1 torr, so the conversion from that would be 1 atmosphere is 760 millimeters of mercury. Alright, so we can't allow ourselves to get tripped up by units here. There's a few different pressure units that we'll all use, so we should know how to convert all of them, especially into atmospheres, which is the one we need whenever we're using the ideal gas equation. So 0.954 atmospheres is the pressure. And so then when we multiply this out to get the number of liters, it comes out to 11.6 liters. Okay, so that's the volume that we get when we react 3.08 grams of lithium with water. Okay, so that takes us to the end of this week's homework review. Any questions that you have beyond this, or anything that you want me to clarify from what I go over, of course you can please contact me either in person or by email, and I'd be happy to go over that with you. Okay, I'll see you guys in class later today, and have a good rest of your day.